Good morning, everyone. Mr. B back here again today. We're going to be going on to our next lesson, which is now on earthquakes. So we've wrapped up volcanoes. We did our thing on volcano legends and myths. We talked about types of volcanoes, the three different kinds, and we looked at volcano hazards as well as doing a write-up on Peyrecoutine at West St. Paul. So now we're going to jump into our second topic of three, and this is earthquakes. Very much related to volcanoes, but slightly different. And we're going to go through a few different lessons. There'll be some labs for you to do, including the earthquake structure lab. But please follow along with the note-taking guide today to make sure you get all the information you need. Now, first of all, an earthquake starts when two plates slide or slip past each other on what's called a fault line. So if you look at the picture on the right, we have a road in the country, and now we have a breakdown of what it looks underneath. Now we have different layers of the earth, as you can clearly see. We have layers of bedrock, layers of dirt and sand, layers of mud, and then of course our top layer. Now, you might notice that there is a crack here. Now this is called a fault line, and these cracks go all the way through our crust. And it's these fault lines which are the big factor in why earthquakes happen, because every now and then these fault lines, due to pressure, try to slip or slide past each other, and that causes the earth to shake. So a fault line is simply a boundary line between two tectonic plates. It's where two tectonic plates meet. Now, if I'm going too fast, just simply pause the video, go back, do whatever you need to do to get the information down. Now, just like with volcanoes, we had volcanologists. With earthquakes, we have seismologists. So these are scientists who specifically study the movement of the earth, including earthquakes. They use special machines called seismographs to record earthquakes. So you see the seismologist on the right there, he's looking at a printout, and it almost looks like a bunch of lines going up and down. And that's a printout that would have come out of what's called a seismograph. Now, a seismologist is just simply a scientist who studies earthquakes. Now, this is on the very basic level what a seismograph could look like. The ones that we use to actually measure earthquakes are much different than this. Generally speaking, what it is a writing device suspended on a platform, and as the earth moves, it moves the pendulum up and down. This is what a more scientific one would look like, and inside there is a printout. Nowadays they're all digitally done, which sends readouts of how much movement there actually is in the earth. So a seismograph is just simply a machine that's used to measure the strength of earthquakes. Now, the seismograph, and sometimes it's known as a seismometer, it's the same thing. It must be attached to solid bedrock in order to feel the vibration from a quake. So if you look at the picture there, the bedrock is a hole dug deep inside the Earth's crust, the bedrock, and the seismograph machine is placed deep inside there with cables connecting it to the surface to give us readouts minute by minute, second by second actually, of what is actually going on there. And seismologists study these all day, especially in places where we know earthquakes occur, to give us indications and warning signs that maybe a large one is coming, and for people to take precautions. Now, this is what's called a seismogram, and this is the printout or readout that comes out of the seismograph. In the sort of pioneering days of earthquake science, they would actually have printed paper on an actual paper. Now it's all printed digitally. So this is essentially just a readout or a piece of paper that is a record of what the seismograph takes. So you could see on the vertical axis, the horizontal axis right here, it says seconds. So that's how quickly these things are occurring, between 0 and 15 seconds. And on the vertical axis, it's how much sort of force is being applied. So you can see right around, right around 4 seconds, just under 5 seconds, it was a huge burst of energy, and then it sort of slowly dissipates from there. Now, seismologists use what's called the Richter scale. Now, the Richter scale is a scale that describes the magnitude or strength of an earthquake. So when we talk about how strong an earthquake is, we're talking about the earthquake's magnitude. So the Richter scale is used to measure the strength or magnitude of an earthquake by measuring the seismic waves. And we're going to talk more about those waves in lessons to come. So what happens when these plates push together is it sends out strong seismic waves. And the seismograph measures these waves and records them on a seismogram. The seismologists then use it and compare it to what's known as a Richter scale. Sometimes they'll measure what are called aftershocks. Now, these are just little earthquakes that happen after the large first one. Now, here's a sample of what the Richter scale looks like. So it goes from 1 to 9, 1 being 0 or 1 being the most light earthquakes and 9 being catastrophic. So anything from 0 to 1.9 on the Richter scale, you won't even know it. You could be sitting in your room at home and you wouldn't even feel anything from 0 to 1.9. You would need a seismograph to detect it. If it's a 2 to 2.9, so in that 2 to 3 range, hanging objects will swing. So you could be sitting in your room at home and you may notice that the lamp that's hanging from your ceilings is swaying back and forth. Or maybe the cord for your drapes in your room or your blinds, sorry, my camera's a little off here, might be swaying from back and forth. But that's it. From 3 to 3.9 or 3 to 4, it feels like a big truck or train is passing by your house. You guys, if you live near a train track, or even here at West St. Paul, when big trains come by our classroom in the portable, sometimes you can kind of feel some vibrations going on. That's what it would feel like from a 3 to 4. Now, 4 to 5 is when we actually start to get some real damage. And so 4 to 4.9, windows might break, and unstable objects will fall. So if you have a shelf that's not properly secure, it could come off. If you have stuff on your tables, they could shake off, and it will cause windows to crack. When you get into the 5 to 5.9, or 5 to 6, this is when things really get bad. Furniture will start to move around, so things like big heavy tables and kitchen islands will start to shuffle around the room, and big chunks of plaster can come off your wall, or drywall can crack as well. So you could be sitting in your living room at home and you'll notice the walls will start to crack, your bed will start moving all around the room. It's pretty serious at this point. A 6 to 6.9, or 6 to 7 essentially, is damage to well-built structures and severe damage to poorly built ones. So your houses at home would be considered, by world standards, well-built houses. So you're going to see damage, big cracks in your wall, parts of your ceiling could come down. It's really getting severe. And if you have a poorly built structure like most of the world has, that your house is probably coming down at that point. So a 6 is probably not big enough to completely topple your house, but it'll damage it severely. But if you have a poorly built house, it'll definitely topple over. 7 to 7.9 or 7 to 8. So this is where even well-built buildings like your houses will come off their foundations. There will be cracks in the earth that will open up on roads, and any pipes underground like sewer pipes will start to break. If it's an 8 to 8.9, this is where things are almost completely destroyed. So you'll have bridges will come down. There's almost no structures left standing. And if it's a 9 or over, we often say this is total destruction. You will actually see the wave moving on the surface. So when we talk about surface waves in one of our next lessons, we'll be talking about something known as L waves, and those are the ones that actually go on the surface. So, for example, this is a earthquake that happened, in Indonesia. So what you see here is the two buildings are completely. One on the left is completely come down. The one on the right is still standing, even though it's damaged beyond repair. It would need to be bulldozed and rebuilt. But certain buildings can withstand more than others. So which building do you think was built better? Obviously A or B. So in this case, clearly B was built slightly better than A, although neither of them fared very well. Now, this railway line used to be straight. Unfortunately, it was built along a fault line and was twisted during a quake. So those are solid solid iron railway ties. And look at that, just bent in like it was nothing. That's the sheer force that these earthquakes can have. This fence used to be a straight line, so you can see that the fence at one point was connected, but being on a fault line, the entire Earth actually moved and shifted it from one side to the other. Now, there are ways to what we call quake-proof your house, and many countries who find themselves on fault lines will do this. Houses built in California, for example, which are on a very famous fault line called the San Andreas fault line, have done a lot of these modifications to their houses. So on your last page, I believe it asks you to list or draw some of these. So the first thing that a lot of these houses will do is have hollow concrete bricks designed to cause minimal damage if they fall. So while they are concrete on the outside, they're hollow on the inside, which means if they break, if they fall, they're going to sort of shatter into lots of pieces and not like crush things. The roof's made from reinforced cement, so it's a lot stronger roof, less likely it's going to buckle or break. Reinforced steel corner pillars. So what they do have here is they have steel pillars that go deep into the earth to give the house more structural safety, and springs can be attached to homes as well to add a little more flexibility so the house doesn't sort of crash over, it can kind of move a bit up and down. And foundations made of stone largely from the remains of destroyed houses. So some of these things are very useful to help keeping your house somewhat structurally safe. It's not going to be perfect, but for smaller earthquakes, it'll definitely keep it a lot better than others. Now, guys, that's it for today. I want you to make sure your note-taking guide is filled out. You can begin working on your earthquake structure project whenever you feel like. Please watch the attached video on how to go about that project. But otherwise, guys, we're going to keep moving on with earthquakes. We're going to talk about seismic waves, the Earth's layers, and how to detect and locate earthquakes in future lessons. Talk to you soon. Bye now.